Hello guys, welcome to another video from AutomataTheory channel. In this video, we're gonna solve the the question number 10 from Sipser textbook, and this question is also about NFA, like actually three last question that I solved for you. And in this question, actually you're gonna learn about star operation in NFA, and knows that the regular languages are closed. Actually, the class of regular languages are closed under a star operation, and we're gonna see this and actually train this with some example that we have in Sipser textbook. So that's it, guys. Let's go. Okay, guys, as you can see here, this is the question number 10. Use the construction in the proof of Theorem 1.49 to give the state diagram of NFAs recognizing the star of the languages described in actually part A, B, and C, that we will see them later. But first, let's take a look at theorem number 1.49. This is the theorem. The class of regular languages is closed under a star operation. The proof idea is that we have a regular language A1, and we want to prove that A1 star also is regular. The idea is that actually we will construct an NFA for language A1, and all we have to do is that actually define some new epsilon arrows from our acceptable state in N1 to start the state of N1, and before that we're gonna define a new starter state, as you can see here, this one. And also this one is our acceptable state, and after that we define a epsilon arrow to a starting state of our first NFA that we construct for this language. So all we have to do is that define these arrows from our acceptable state to a certain state of the NFA that we constructed before, and after that define one new starter state that is our acceptable state also, and define one new epsilon arrow to a certain state of the NFA that we constructed here. So this is the idea that you can see here. But also, let me tell you something. There is one bad idea to actually prove that, and in this idea we don't define this new actually a starter state here. We just actually replace our starter state with an acceptable state. Actually, we made this one new acceptable state, but this one is wrong. This is not a good idea. And there is one example that we will see later that is show us this proof, and this idea is wrong. So yes, that's it. This is the theorem, and now let's back to question. In part A, actually we're gonna solve the part of the question number 6 that we solved before, but with this theorem and with this idea. The first part is question 1.6 part B, and then part J, and then part M. That I write all of them in my notebook. The first part is that L that is equal to W, that W contains at least 3 ones. So actually this one is easy. All we have to do, we're gonna actually construct a DFA with 4 states. Actually, in the first state, the number of ones that we have is 0. So, and after that here is 1, and then actually here is 2. In this state here we have 2 ones, and after that here we have 3 ones, and based on our condition, this is our acceptable state here. So yes, that is. And after that, the number of ones doesn't matter for us, so it will be like this for ones. But for zeros, actually if we want to construct an NFA, the number of zeros, we know that in this question the number of zeros doesn't matter for us. So actually this is a good NFA that we can construct for this language. But if we want to construct a DFA, actually we have to define the arrows for 0. So, and we know that in this question the number of 0 doesn't matter for us, so it will become like this actually. Yes, and yes. So this is the DFA that we construct for L, and now we want to construct a new NFA that recognizing the language L star. All we have to do is that we define a new starter state actually, and now we know that this is our acceptable state also. So it will become like this, and after that we define a new epsilon arrow to a starter state of L. So it will become like this, and after that all we have to do is that actually rewrite or regenerate our DFA that we constructed before. So it will become like this actually, yes, here it, and yes, this is the DFA that we have before, but we have to notice to this part that we have to also define a new epsilon arrows to the starter state that we have before, like this. And yes, as you can see, this is the actually NFA that we construct for the language in part A. And now let's go for next part actually. The next part, if I want to show you, yes. Part B says that languages that W contains at least two zeros and at most one. We know that the class of regular languages are closed under intersection, and as you can see, we have intersection actually. We can assume that our language is W contains at least two zeros, and another language is that W contains at most one ones. And after that, we construct a new DFA for the intersection of L1 and L2. And after that, we can construct a new NFA for actually a sort of intersection of L1 and L2. So now, first, let's define L1 and L2. L1 is that W contains actually at least two zeros, yes, like this. And L2 is that W contains, again, at most one, like this. So actually, we split this language into two parts, L1 and L2. Now first, let's construct the DFA for L1. For L1, our DFA is something like this. We must have at least two zeros. Actually, this part is really like the part A that we solved together. So if we want to construct a DFA for this part, it will become like this. We know that the number of ones doesn't matter for us, so their arrows will be something like this, and all we care about is the number of zeros. And we know that after that we reach two zeros. After that, the number of zeros, it doesn't matter for us. So after that, we will stay in our acceptable state. So the final DFA for language L1 is something like this. Yes, this is for L1, and now for L2. L2 says that W contain at most one ones. So we will construct our DFA like this. Actually, we will continue to add ones until we reach one. So these two states here are our acceptable state. But after that, if we reach this condition and actually somehow go over this condition and we have two ones, after that we can't accept our state. So it will become like this, and we know that after this condition, the other state that we have like that we have 3 ones, 4 ones, 5 ones, or something like that, we can accept any of these languages. So we will stay there like this, and in this language the number of 0 doesn't matter for us. So if you want to define the arrows for these zeros, it will become like this. And yes, This is the DFA for language L2, and now we have to construct the DFA for intersection of L1 and L2. And actually it will become something like this for intersection of L1 and L2. The number of states, we know that is the Cartesian product of number of states in L1 and L2. And in L1 we have 3 states, and in L2 we have 3 states. So the answer is 9 states. The final DFA that we can construct for intersection of L1 and L2 will have actually 9 states. And it will become something like this. Actually, yes, and these arrows are for number of zeros. We know that anytime that we see ones, we will go to our next state somehow. So it will become like this. Yes, and we have a state here and here and here, and after that we will have a state like this again. And also if we see zeros, we will go over our condition like this. Yes, and finally these 3 states here, here, and here, and between them we have the arrow for 0. And we know that in this state that we have here, actually the edge states, better I say, if we see a 0, we will stay in our state, or for this state, if we see a 1, we will stay there like this. But in our final state, if we see a 0 and 1, we will stay there like this. And yes, this is the DFA for intersection of L1 and L2. And now we have to actually show the accepted state. The language L1 says that we must have actually at least 2 zeros. So our accepted state can be actually this state. Actually, let me see again. W contains at least 2 zeros. So we will accept this state, and this state, and this state. And for L2 says that W contains at most 1. And we know that for this language, we will accept this state, actually, or better I say this state, and these. And sorry, we don't. And but yes. And this, and yes, that's it. And the intersection of these languages is these 2 states here. So these 2 states are our accepted state actually. And now we want to construct a NFA for the star of this language. So it will become actually something like this, and we will define some new epsilon arrows to our start state. So for a star of intersection of L1 and L2, it will become like this. We define epsilon arrow to our start state of DFA that we construct, something like this actually. And before that, we will define a new start state that is our accepted state like this. And this arrow will become our epsilon arrow for our new start state to our old start state. And yes, it will become something like this. And yes, this is the NFA that we can construct for a star of intersection of L1 and L2. And now let's go for part C. Part C says that our language is equal to the empty set. We know that in empty set we can't accept any strings. So if we want to construct a NFA for this language, it will become like this. Yes, that's it. Because in NFA there isn't any actually rules that we must define the arrows for any alphabet that we have in our alphabet set. So it will become like this. But actually we want the NFA for L star. So all we have to do is that we know that here we don't have any active state, so we don't have to define some new epsilon arrows. And yes, that's it. All we have to do is that we must define a new start state that is our active state also, and define a new epsilon arrow to the last start state that we have. So yes, that's it. This is the NFA that we can construct for L star, and yes, we solve every part of this question. I hope you guys enjoyed this video and learned some new things about NFAs in this video. If you like this video, like it and leave a comment for me. I will read all of your comments, and if you want, you can subscribe to my channel, and this is a big motive for me. And yes, that's it. Have a nice day, guys. Goodbye.